1. Okay, welcome to Math 389 Advanced Analysis. This is lecture 6. And so some of you are starting to tell me what you're interested in doing for your high-level advanced write-up, as well as what you want to do for the math outreach. As you start telling me what you're interested in, that's going to impact the lectures I do for everyone. I am not envisioning that we will be meeting every day, but when somebody wants to do, something, if I have something useful to say about it, I will. If you are coming in late, we were talking about moving the startup class back 2 or 3 minutes, just because this way people can be a little bit more relaxed, not rushing through campus. I remember what it was like when I was a senior having to do that. So today I want to talk about the exponential function. I want to talk about trigonometry, matrix exponentiation, and generalizing formulas, and then I'll use the concept of the mean as a nice way to end the day. And again, this is drawn from the fact that somebody was interested in stuff like this, which has connections with physics. So who are my physicists here? Okay, so you've seen matrix exponentiations. Have you seen any rigorous theory behind why all this works? Okay. All right, so I don't know if I think we talked briefly about this before. So we've defined this function exponential of x, and you use a colon in front of the equal sign to indicate this is a definition. To be the sum, n goes from 0 to infinity of x to the n over n factorial. What's nice about this is this makes sense for any x. You give me any real x, any complex valued x, this makes sense. And of course, we write e to the x. And as soon as we write e to the x, this is suggestive, right? E to the x times e to the y is e to the x plus y. But technically, if I give you exponential x, exponential of y, that is the sum, n goes from 0 to infinity, x to the n over n factorial, and then the sum, m goes from 0 to infinity, y to the m over m factorial, versus the sum, let's say k goes from 0 to infinity, x plus y to the k over k factorial, which would be the exponential of x plus y. What should be true about those two expressions? So what should be true? They should be the same, right? So we need to prove that they're the same. So what we have is we have a double sum. So we have 2 ways to go. We can either show that the double sum equals the single sum, or show that the single sum equals the double sum. Does it matter which way we go? No, because whichever way you go, just reverse it, and that's the other direction. Does one way seem more natural to you?
Left to right.
I think so as well. I think it seems more natural to start off with the product of the two exponentials and show that it equals the exponential of the sum. And again, this is just hardwired in terms of which we think of. So let's think about what's going on. So the question is always, when can things be justified? So the left-hand side, it's the same as the sum n goes from 0 to infinity, the sum m goes from 0 to infinity, x to the n, y to the m, over n factorial m factorial. So much of mathematics is about pattern recognition. When you see n factorial, m factorial, does that remind you of anything? It reminds you of a binomial coefficient, that when we think about what's going on, we have lots of x's and y's to various powers. Let's group them so that all the x's and y's, we're going to take them such that the sum of their powers is fixed. So I claim that this is the same as the sum, k goes from 0 to infinity, the sum, L goes from 0 to k, x to the L, y to the k minus L, over L factorial, k minus L factorial. So this is the big step that needs to be justified. So what theorem am I trying to use? It's related to rearrangement, but so I need absolute convergence. But there's a thing you should have hopefully seen in maybe real analysis or multivariable calculus, although probably not proved in multivariable calculus. I need something to justify this kind of rearrangement.
Oh, simplicity.
So if I had simple regions, but this is like the Fubini theorem is lurking in the background. And so if people are looking for something to write about, doing this rigorously and putting in the Fubini theorem. And Fubini basically tells us we can switch orders of summations, we can regroup things if things are absolutely convergent. So if absolutely convergent, can regroup. And this will be related to like a Fubini theorem. But that's the step that has to be justified. Is everything going to be absolutely convergent? If I put in absolute values, will that sum be finite? Yes, because the exponential function grows so rapidly. And we'll talk about that in a little bit. So for now, we'll do what you always say. Yeah, let's just assume that this is okay. Argue, and then go back and justify why everything was okay. So now we have it equals, the sum, k goes from 0 to infinity. The sum, L goes from 0 to k. And then I'm going to put the L factorial, k minus L factorial here, x to the L, y to the k minus L. So is everybody comfortable with what I'm doing? I want all the x's and y's such that the sum of the exponents is k. And so if I have L x's, I have to have k minus L y's. When you look at this, everybody's really quiet. You can hear screaming what's missing, right? What's missing? K factorial. And so are we allowed to just put in a k factorial? I'm sorry? Yeah, as long as we divide by it. And I'm going to put the k factorial that I need to divide by outside the sum. That's fine. And the reason I want to do it this way is now this bracketed quantity is very nice. What is that bracketed quantity?
X plus y.
Yeah, just x plus y to the power of k by the binomial theorem. So now we would get that this is just, the sum, k goes from 0 to infinity, x plus y to the k over k factorial, and that is exponential of x plus y. And that would finish the proof. So it was, identifying a correct one to put in, grouping things properly. All that we have to do is justify that if we have this sum, we can rearrange the terms. And this is where you need some kind of result about things converge absolutely, so you can add them in any order. And so let's get some estimates on n factorial. And for those of you who have taken multiple classes with me, I apologize. I love doing estimates of n factorial. A lot of times what you want to do is you want to get a sense of how clever do you need to be. I was supervising a honors thesis at Princeton years ago with Professor Wiles, and a student needed to use Bayes bound for Kloosterman sums. And this is really nice result in algebraic geometry. You have almost square root cancellation. The proof is involved. I do not understand the proof. I have not really learned enough algebraic geometry. That's fine. We didn't need the full strength of Bayes bound. We just needed a small power savings. And one of my advisors, Henrik Evanius, had shown me a nice counting on your fingers argument to show that there was a power savings by looking at a moment. And so it was important to realize that we don't actually need this full, most powerful result. Now, when you're writing papers, you often put in the best result. I actually like to have a free parameter. And then at the very end, you can say, we've got it as a function of delta. The best known result is delta equals 13/27, and therefore we win. And then if there was a mistake in the best paper, then you immediately can fix yours and say, oh, 13/27 was not quite right. Let me put in now the second best result, which is now the best result. So it's good to get a sense of just how deep a result is, what is really needed. I don't need the best result on n factorial. I just need some weak results. So I claim n factorial, which is n minus 1 dot 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 3 times 2 times 1 is greater than equal to n halves to the n halves. Is everybody comfortable with a bound like that? Maybe I have to worry a little bit if n is not even. I don't care. I should be more than safe enough like that. Because just look at the last half. Everything in the last half is at least n halves. I have n halves of them, so I have something like this. So if I look at a sum, n goes from 0 to infinity of x to the n over n factorial. The sum m goes from 0 to infinity of y to the m over m factorial. And I take the absolute value. That's going to be less than or equal to the sum n goes from 0 to infinity, sum m goes from 0 to infinity, absolute value of x to the n, absolute value of y to the m, and then n factorial. That's going to be at least n halves to the n halves. And then we'll have at least m halves to the m halves. So that would be the sum n goes from 0 to infinity. All right, absolute value of x to the n over n halves to the n. That should be, I think, square root of 2 absolute value of x to the n over n to the n. And something similar for the y sum. Oh yes, sorry. So yes. So let's do square root of n, square root of m. Thank you. Are these going to converge? Will those sums converge? Yeah. If I look at just one of them, this is root 2 absolute value of x over square root of n to the n. If n is greater than 2x squared plus 1, this is less than 1 in absolute value, converges by comparison test with the geometric series. I've got tremendous translation. I just want this expression to be less than 1, then by the geometric series it works. So once n is greater than 2x squared plus 1, I'm going to be fine. So I'm not worried about things converging absolutely. I have tremendous convergence. And again, I'm doing the simplest estimates I can do that will guarantee me convergence. N factorial is more than n halves to the n halves. But this is all I need. So I'm not going to, go crazy. Okay. Now, famous formulas. E to the ix is cosine x plus I sine x. How many of you have seen this? So this is one of the greatest formulas in all of mathematics. Why is this true? Okay. So cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And this comes from What's the derivative of cosine of x? Minus sine of x. And my mnemonic is you have to remember where to put the minus sign. It's with the minus sign. And what's the derivative of sine of x? So once you have this, if you use your Taylor series expansions, then everything is fine. But how do you know the derivative of cosine is minus sine? The derivative of sine is cosine. So one possibility is, let's erase this and let's rewrite it as a definition. So if I define sine and cosine like this, and I can justify differentiating term by term, then the derivative of cosine is going to be minus sine, and the derivative of sine will be cosine. So if I make that a definition, then I'm fine. But now I've defined sine and cosine in that way. So do you want to define sine and cosine by their Taylor series? Or are we defining them in terms of a triangle? It's a non-trivial question as to how do you define things. We are so used to just manipulating quantity sometimes without stopping to think, what are we manipulating? How would you calculate the derivative of sine or cosine? If you have the Taylor series formula. So again, I don't mean to imply that you come from inferior schools. I'm sure you all learned calculus as, kindergartners, right? And had that available for you when you got to geometry and trigonometry, right? But most people don't have that. So can you imagine what it must be like to do trigonometry without knowing calculus? How would you define sine and cosine?
The sides of the triangle.
Yeah, by the sides of the triangle. So that's what we got to go back to, right? Here is, maybe our unit circle. Radius, here's the point 1, 0. Here's the point 0, 1. Oops. And then here's 1. And then this would be theta. This would be cosine theta. And this would be sine of theta. And so we can define functions sine and cosine like that. As a nice exercise, you can prove angle addition formulas. You can prove, the sine of x plus y is sine x cosine y plus cosine x sine y. And cosine x plus y is cosine x cosine y minus sine x sine y. Does this seem familiar? So as a nice exercise, if I give you, something like this, here's the angle x, here's the angle y, and then here would be cosine x plus y. Over here, this would be the sine of x plus y. And I'm going to assume 0 less than equal to x, y less than equal to x plus y, less than equal to pi halves. Now, of course, I'm even in trouble because I'm now using something like pi halves, but we'll get to that in a moment. So I'm just doing this for the sake of making the drawing nice, that I'm going to assume x, y, and x plus y are all at most 90 degrees or pi halves radians. And if you can prove the angle addition formula there, then you can extend it to other things. Anybody remember how you would prove the angle addition formula?
I remember something about multiplying some kind of matrix. I kind of forgot, like, I think it's just rotation. Something like that. Turn out okay, but I kind of forgot.
So let's see if I can move this over. Oh yeah, okay. So the question is, did I accidentally make this? Oh, okay. So what do you think I need to do for geometry proof? Draw, right? I've got to draw an auxiliary line. What am I going to want to get with my auxiliary lines? Right angles, right triangles. So a really good choice is, is to come in like this over here and then come down like that. And so now let's start giving things names. A, B, C, D. What's the length of segment AC? Cosine Y. What's the length of segment CB? Cosine Y sine X. And so that gets us up to height here. So what I can do is I now need to get this little thing over here. So I'm on A, B, C, D. So I now need an E. So I can blow things up. Here's E. Here's D. Here's C. What can you tell me about CD? What's the length of CD? Sine Y. So I know this is sine Y. I know this is a right angle here. Do I know any other angles in this triangle? So angle CD, which angle?
Angle
Angle C, CDE. Okay, so CDE you're claiming is X. Why is that X? Similar triangles. So does everybody see that it's X? So if this is X here, this would be 90 minus X here. This would be 90 minus X here. This would be X here. Then this would be 90 minus X. So then that would be X. So yes, that is angle X. So now that we know that, what can you tell me about the length DE? We know we have the angle X over here. We know the hypotenuse is sine of Y. So what is DE? Yes, but I'm going to write it as cosine X sine Y. And so now I need more letters. Let's call this F over here. So let's, I haven't used orange yet. Here's orange. So we'll call this F over here. So DF would be the sine of X plus Y, and that's going to be DE plus CB. You agree that DE plus CB is going to be the same. And that is going to be DE is going to be cosine X sine Y. Okay, so I wrote things in the wrong order. Oh, well. Plus cosine Y sine X. Or just writing it better, sine X cosine Y plus cosine X sine Y. So that is a proof of the angle addition formula for sine in the special case when the angles add up to. Does this remind anybody of high school? So you can prove this stuff, okay? So we do have a formula for the angle addition. Okay, now we want to calculate sine prime of X. If you're willing to assume sine and cosine are differentiable, let's let f of X be sine squared x plus cosine squared of x. What does that equal? It's just 1. So f prime of x is 2 sine x times sine prime of x, whatever that is, plus 2 cosine x cosine prime of x equals 0. Can you give me a good value of x to use? What's a good value of x to use? This is true for all values of x. I'm sorry?
Pi 4.
Pi fourths. Okay, so if I use pi fourths, I would know what sine and cosine of pi fourths are, but I don't know what sine prime and cosine prime of pi fourths are.
You'll know if they're opposite.
I'll know they're opposite. So a good choice is, there's two good choices. If we give you a good choice for x. Zero and pi over 2. If we take 0, we get 2. What's the sign of 0? That we know. And so when we do that, that gives us 2 cosine of 0, cosine prime of 0 equals 0. Therefore, cosine prime of 0 equals 0. If we take pi halves, we get the sign of pi halves is 1. So we get 2 sine of pi halves, sine prime of pi halves, plus 0 equals 0. So we get sine prime of pi halves is 0. So if we assume sine and cosine are differentiable, we know very easily what cosine prime of 0 is. We don't know what sine prime of 0 is. So if we want to calculate a derivative, so if we want to calculate, say, sine prime of x, this is the limit as h goes to 0 of sine of x plus h minus the sine of x over h. This is the same as the limit as h goes to 0, sine x cosine h plus cosine x sine of h minus sine of x over h. What should we group together? Yeah, so this will be the limit as h goes to 0. I can pull out the sine of x. I forgot to leave room, so I'll have to do it like this. Sine of x, limit as h goes to 0 of cosine of h minus 1 over h plus the limit as h goes to 0 of, I can pull out the cosine of x, and I'll have sine of h over h. So I clearly want to do something given how much space I've left. What does cosine of h minus 1 over h look like? So I've got cosine of h minus 1 over h. That should look like something you've seen before. Any thoughts? I can prime you by writing things in a special way. Nope. 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 So you know why you can't use L'Hopital? It requires knowing the derivatives of sine and cosine. Now, you might say, since we are working on a circle, we should be able to use circular logic, but no. That is not allowed. So what does cosine of h minus 1 over h look like? That should, so much of math is pattern recognition. It's nice that we have a class that is a prerequisite for nothing. We can afford to take time and really think about this. Does this look like anything you've seen? How else could you write 1?
Cosine squared.
I'm sorry?
Cosine squared, sine squared.
You could, but there's a better way of writing 1.
Oh, it's not 1. Oh, sorry. Cosine 0.
Yeah, I could write this 1. Let me change it and write cosine of 0. And then instead of writing cosine of h, what if I write that as cosine of 0 plus h minus cosine of 0 over h? What does that look like now? Yeah, so then this just becomes sine of x times cosine prime at 0 times cosine of x. Now, sine of h. How could I rewrite the sine of h? I could write that as the sine of 0 plus h. And what should I subtract? Sine of 0. And so when I do that, I then have sine prime of 0. So we've just shown if you can differentiate sine and cosine at 0, you can differentiate sine anywhere. By a similar argument, you can show you can differentiate cosine anywhere. So which of these two is the difficult one to get? Cosine prime of 0 or sine prime of 0?
Sine.
Yeah, why?
Because it's 0.
So why is sine prime of 0 harder than cosine prime of 0? It's not 0, exactly. So this is hard as it is not 0. If I rescale things, when you go from radians to degrees, you multiply by either 360 over 2 pi or 180 over pi or pi over 180 or 2 pi over 360. You multiply by one of those depending on who taught you, right? Is it hard to convert from radians to degrees and back and forth? No. If you measure things in radians versus degrees, you will get different derivatives. If you have a non-zero number, what's the nicest non-zero number you could have? 1. And that's why we use radians. This is another reason for radians. If we work in radians, sine prime of 0 becomes 1. Cosine prime of 0, we've already established that that equals 0. We already know what that is. It's everything in trigonometry comes down to, can you calculate sine prime of 0 is 0? I'm sorry, the sine prime of 0 is 1. How many of you have done this before? Okay, that's why we have a class like this. Okay, so on hold. Okay, so we'll put the matrix exponential on hold a little bit, just to finish things off. We need to calculate sine prime of 0. Anybody remember how you calculate that? So we need the limit as h goes to 0 of sine of h over h. This is the key limit. Everything in trigonometry follows from this. And no, we cannot use L'Hopital because we don't know the derivative of sine. How can we calculate this? There is some geometry argument, yes. There are two types of geometry arguments we can use. What shape are we going to use? Right triangle, related to what object? It's got to be, somehow there's got to be a circle. So choose pi so that area of a circle of radius r is pi r squared. There is some constant such that that is true. If I basically rescale a circle, the circle is going to grow proportional to the square of the radius. Just think about it as changing from measuring things in feet to measuring things in meters.
So are we redefining pi?
Well, so I'm saying there is some constant pi
Yeah.
such that this is true.
Yeah.
And then we can numerically calculate pi. And how could we calculate pi? We can do the inscribed and circumscribed n-gons, regular n-gons that will converge. And so what we can do is, it's often better to use areas than perimeters. I will risk making a comment from multivariable calculus. If you want to find lengths of curves, do you remember those formulas? We have to be careful with the square root of 1 plus dy over dx squared inside the square root, because ds squared is not dx squared plus dy squared. You got to be a little bit careful. So we have to be a little bit careful here as well. So what if I take an n-gon? So do you want to do an n-gon or a 2 n-gon? Yeah, let's be safe. So we'll do a 2 n-gon. So we have some angle over here, right? So we'll call this so if we have a 2n gone, how many of these triangles will we have going all the way around? We'll have 2n of them, right? So 2n times the area of triangle Tn, what does that converge to? Pi r squared. And so it'll just be 1 because we'll choose radius 1. What's the area of triangle Tn? So we have to choose, of course, what the angle is. So this is going to be theta 2n over 2, theta 2n over 2. So what is the base? What's the height? Cosine theta 2n over 2. We're assuming unit circle. So what does the cosine of theta 2n over 2 represent? That's the height. So this is the height. And now we need the base. What's the base going to be? So theta 2n over 2. And then we multiply by 2, right? But we have a triangle, so we have a factor of 1/2. So we'll see whether or not we really needed to have the 2n versus n. So we were going to get 2n cosine theta 2n sine theta 2n each over 2 converges to pi. Anybody recognize what we have here? Double angle formula. So this is going to be n times the sine of theta 2n. Right? Now let's show off a little bit. 2 and a 1/2. Because I have a theta 2n, so I want to have a 2n over there. So this is going to be equal to 1/2. Then I'm going to have a sine of theta 2n over 1 over 2n. And this converges to pi. So how does this help?
because theta 2n is just pi over n.
Why is it pi over n?
Then you need to define the radius.
So it's worth really thinking about how things are defined. So I can move the 1/2 over and put a 2 pi over there. What should we call the total angular measurement? I can move the 2 pi over, and this becomes the same as the sine of theta 2n divided by 2 pi over 2n goes to 1. So if we define the angular measurement to be 2 pi, we now have our limit equals 1. So if we define the angular measurement to be 2 pi, where pi is coming from the area of the circle, then this limit is 1. So now define angular spread to be 2 pi, we get the sine of 2 pi over 2n over 2 pi over 2n goes to 1. That's the limit we wanted. We technically only did that limit at specific integer multiples. It's supposed to be this limit no matter what. But if the limit exists, it should exist no matter which way you take it. I'm trying to just show you right now just how subtle and difficult these problems can be. Did you guys actually define trigonometry properly? Did you do differential trigonometry properly? Or did we slip this by you? How much is actually needed to prove these derivatives? It's actually non-trivial to prove the derivative of sine is cosine, the derivative of cosine is negative sine. It all comes down to the limit of sine of h over h as h goes to 1. And just thinking very carefully, where are things defined? Now that we have that, then things are in much better shape. And so what we would want to do now is if we have e to the I x, yes?
I would already define the area to be pi r squared.
So when we define the area to be pi r squared, we haven't said anything about the perimeter. We haven't said anything about the angular measurement. If I choose the angular measurement to be 2 pi, then the limit becomes 1, and all my derivatives work out nicely. And what was nice then is that the angular spread is the same as the amount of arc that you've traveled on the circle. So things work out very nicely. What day should you eat pizza? What day should you eat pizza? Pi Day. And when is Pi Day? March 14th. Does anybody know which day competes with Pi Day? Nobody knows about the competition that Pi Day has? It's in June.
June 28th.
June 28th. Yes. Anybody know what June 28th is? It's Tau Day. So Serge Lang once said that if the Greeks had been really intelligent, they would have created 2 pi. Which is the more fundamental constant, pi or 2 pi? How many of you have done complex? Well, not that many, huh? Okay. In complex analysis, you have a lot of integrals that involve 1 over 2 pi. So for a lot of things, 2 pi is the more natural constant than pi. It's, do I care about the perimeter? Do I care about the angular measurement? Or do I care about the area? Who are my physicists again? Okay, 1 over 4 pi epsilon naught. What am I thinking of? E&M, electricity and magnetism. Why is the constant written as 1 over 4 pi epsilon naught?
With Gauss's law.
Okay, but why would you write the constant as 1 over 4 pi epsilon naught?
The solid angle, the 4 pi.
Yeah, it's talking about the surface area of the sphere. That's where the 4 pi comes from. That's why they're writing the constant like that. So normally it's pi versus tau, but sometimes you might even have like a 4 pi coming. But as soon as that comes in, you have all the other higher dimensions. And so they normally just lose out and it comes down to pi versus 2 pi. But what I wanted you to get out of this is just, we have to be really careful with how we define things. It's so easy to accidentally just manipulate and maneuver with things without recognizing what was required to get to this point. It is a lot of work to get to this point. But here I'm just using triangles. I'm just using, things scale nicely, so it's not so bad. Okay, now when we have all of this, now that we have the derivative of sine is cosine, the derivative of cosine is minus sine, now we have the series expansions. Now we have the Taylor series. And now we have e to the ix is cosine x plus I sine x. So now we can use Taylor series. And we can do e to the ix, e to the iy is e to the ix plus y, which is cosine of x plus y plus I sine x plus y. So if y equals negative x, then e to the ix, e to the minus ix is 1, right? So cosine x plus I sine x, cosine x minus I sine x equals 1. And here I'm just using the fact that cosine of negative x is cosine x, cosine is an even function, sine of negative x is negative sine of x, sine is an odd function. You can see those clearly from the Taylor series. You can view this as, of course, cosine squared x plus sine squared of x equals 1. There's Pythagoras. And the other one, of course, is cosine x plus y plus I sine x plus y is cosine x plus I sine x times cosine y plus I sine y. So if I group things together, I'll get cosine x cosine y minus sine x sine y as the real part, plus I sine x cosine y plus cosine x sine y is the imaginary part. And the only way two complex numbers can be the same is if the real parts are the same and the imaginary parts are the same. So really, the angle addition formulas in trigonometry are inherited from the exponential function. It all comes from the exponential function. Then, of course, you could talk about why is the derivative of the exponential function the exponential function? Well, if I can just say the derivative of the infinite sum is the infinite sum of the derivatives, then everything works out. You need to justify that. All right. Now, matrix exponentiation. So remember on the first day of class, we talked about if we want to take the derivative of x to the root 2, we write that as e to the root 2 natural log of x. Or since we're in college, e to the root 2 log of x. Because we don't write natural log anymore as ln. And we said that it doesn't make sense to talk about what does it mean to take a number x and raise it to the root 2th power. I don't know how to do that. I can take x times x, I can do that. I can take the square root of x. I'm looking for number y such that y times y equals x. I don't know what it means to take something to the root 2th power unless I interpret it like this. So if I now give you e to the x, we said this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 dot. So this was a sum of x to the n over n factorial and goes from 0 to infinity. And for what x was this true? So complex. So as long as x was complex, it's true, because n factorial grows so rapidly, it's going to converge. So we're okay for all x in C as n factorial is greater than n halves to the n halves. So instead of using the letter x, let's use the letter A. Can I do that? Am I allowed to use the letter A?
As long as it's complex.
As long as it's complex. Let's say A is a n by n matrix. So the question is this legal? Let's look at it term by term. Term by term, is it legal? Each summand is legal because A is a square matrix. What's the only danger? It doesn't converge. So the claim, I'm sorry? No, converges for all A. So claim converges for all A. And the proof, let M be the maximum of the entries of the matrix. Okay. If I want to look at the maximum element of A squared, how big could that be? What's the largest an element of A squared could be? Worst case.
N times the largest value of A squared.
M times, wait, say that again?
N times the largest.
Okay. This is one of the dangers when you have M and N as variables, is that sometimes it's really hard to hear is someone saying M or N. So the worst case is if you have a matrix that's all M's, right? So there's absolutely no cancellation. It's maximum reinforcement. And then this is just going to be M squared times the matrix of all ones squared. And what's the matrix of all ones? This is going to be the matrix of all n's. So I can pull out an n, and this would be m squared n times the matrix of all ones. What if I gave you the maximum of A cubed? You would just have another one of these matrices. That would be m cubed times n squared. Right? So I still have space. Excellent. I love just enough slides. So if I gave you the maximum of A to the nth, that should be less than or equal to m to, I think, the n minus 1. No, I'm sorry, m to the n, and then should be n to the n minus 1. So if you look at the ijth entry of the sum a to the n over n factorial, n goes from 0 to infinity, that's going to be at most, the sum n goes from 0 to infinity, m to the n, big N to the n minus 1 over n factorial. That's fine. That's going to converge nicely. So everything will be fine. Everything will converge. So we can talk about matrix exponentials. Now, what's exponential x, exponential y?
So
Exponential of the sum. For what x and y is this true? So any x and y, so they can be baseball teams.
at least for all complex.
Okay, at least for all complex. X and y are in complex. What do you think I should now replace x and y with? Baseball teams. Matrices. What do you think? No, we know the matrices have to be square in order for the matrix exponential to make sense. They have to be the same square matrices, otherwise we can't add them. So do you think exponential A, exponential B is exponential A plus B? Not necessarily. That is a real safe answer. Do you think it's always going to be true that the product of the exponentials is the exponential of the sum? What's your intuition?
Based on the arithmetic, it seems like it should apply to any base.
Yes, like danger maybe would come from multiplication, but there is no multiplication here. But when you do the sum of x plus y to the power of n.
So what happens? So let's look at what's going on. This is the sum, n goes from 0 to infinity of a to the n over n factorial. This is the sum, m goes from 0 to infinity of b to the m over m factorial. And over here, let's have more colors. This is going to be the sum, k goes from 0 to infinity of a plus b to the k over k factorial. What is a plus b squared? What does that equal? And then it's either a squared plus ab plus ba plus b squared, or if you want to do it, a squared plus ba plus ab plus b squared. I don't really care which one you write. I want the a squared first. I want the b squared last. We don't know that ab plus ba is twice ab. So what do you think you have to be concerned about here? Commutativity. Can you give me a condition when they're equal? Okay, so when AB equals BA, do I need anything about A squared B and ABA? Or as soon as I have AB equals BA, am I safe? As soon as I have that, I'm safe. I don't have to worry about anything higher, because once I have AB equals BA, I would know A, B, 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 A. I can put all the A's on one side and then all the B's on the other. This is horrible notation, i.e., comma, when we're dealing with complex numbers at square roots of -1 and exponentials. This is called the commutator. The commutator is defined as AB minus BA. We want that to be the zero matrix. And this is called the commutator. So if the commutator is 0, then the proof we gave actually holds. And it holds because we can move all the A's to the left and all the B's to the right. What if the matrices don't commute? Then maybe it's true, maybe it's not. If you had to guess, what would you guess? It's not. And so this is one of my favorite formulas in all of mathematics, the Baker-Campbell-Hausdorff formula. Have any of you ever seen this? Have you seen this in physics?
We were doing this in an independent study last week.
Oh, wonderful. With which professor?
Trig.
Okay, excellent. Were you proving this? Okay, so I mean, this is a non-trivial thing to do. So e to the x times e to the y equals e to the z. This is trivial. Or maybe it's not. So I mean, the question is, if I give you a matrix, is every matrix the exponential of another matrix? If so, I can just define z to be whatever I need. But it's not immediately clear that no matter what I give you, there will always be some matrix z such that e to the x, e to the y is e to the z. I hope there is. But it's not clear that such a z exists. It turns out z does exist, and here is a formula for z. If the commutative of x and y is 0, what do you think this reduces to? Yeah, it just reduces to x plus y. So it becomes really nice in the special case when the commutative is 0.
What are the quick things actually? Are these,
What's this? Is this notation like? Sorry,
Yeah.
oh, no, you can go.
I was just wondering. Is this like a commutator of a commutator, or?
Yes. So this would be, you first commute x and y, and that's going to be a matrix. And then you take that and find the commutative of that with x. And so the next slide, I think, expands things out a little bit for you. And another nice way of writing it. And then there's a natural question you should ask as soon as you see something like this. What is the question you want to ask? The coefficients.
I think there seems to be like a twice, I mean, 2 times relationship.
So again, my daughter has a very strict rule with me. I am not allowed to lie to students or children. I am allowed to mislead. Okay, so I just want to make sure we're all, because reading shopping period is not over yet, correct? You still have a chance to escape? Yes?
No, it's over.
Oh, it's over. Oh. Excellent. Okay. So wonderful. No, so I will be honest that I will be honest, but I can definitely mislead you. I can prime you. I can make you think of things the wrong way. So let's look at the numbers we have. Okay. What numbers do you see here? You look at, what numbers do you see?
1/2.
1/2. Okay, but 1/2 is not the first number you see.
1.
1, 1/2, 1/12, 1/24, and we have some plus and minus signs. 1/360, 1/120, 1/720, and so on. How should I view 1? So I could view it as 1 factorial, 1/1, 1/1 factorial, one more way. 1/something factorial. Yeah, it could also be 1/0 factorial. Those are all, again, we are trying to detect patterns here. 2 1s may not be the same one. If you think about what we were doing, eons ago, we have 1 plus x. This 1 is really coming from x to the 0/0 factorial, and then x is coming from x to the 1/1 factorial. These are not the same ones. They're different ones. How should you view 1/2? How do you want to view 1/2? 1/2 factorial. How do you want to view 1/12?
1/2 factorial times 1/3 factorial.
So 1/2 factorial, 1/3 factorial. How else?
4 factorial over 2.
Other way around.
As in,
2/4 factorial.
yeah, that's right.
Right. Oh, I see. Okay. How do you want to view 1/24? How do you want to view 1/360?
Is this a trap actually?
So I said I would not lie. I said I could mislead. I also did not say I would answer every question. So I will not answer if this is a trap or I'm trying to mislead. Because if I answer, then I have to answer honestly. So how would you view 1/360? 2/6. So you could view it as 2/6 factorial, and the other ways. So for the 1/12th, you had 1/2 factorial times 1/3 factorial. Is there another similar way to get 360? Can I write it maybe as a couple of products of reciprocals of factorials? So 4 factorial is 24. Can I get from 24 to 360? 5 factorial is 120. I could view it as 1/3 factorial, 1/5 factorial times 2. Right? So I will stop here. There definitely seems to be games you can play to get all of these numbers using factorials without doing anything too absurd. Right? There's got to be a lot of math behind this. Right? So for those of you who are doing this in the tutorial, did you see expansions like this with these constants?
We stopped at the 1/12.
Yeah. I mean, the hope is that, you don't have to take too many terms to get good approximations, or that you frequently in physics, you might have, x might be like x times t and y might be y times s, where t and s are small. So high powers are negligible. Have you done something like this? Okay, so, again, I love it talking to other professors here, and by all means, feel free to talk to your professor and say, where do we use something like this? And you might have some kind of expansion where x and y are actually, you have some kind of small free parameter next to it, so that the higher order terms don't really matter. And you might be doing some kind of like asymptotic expansion or whatnot. But there's got to be some deep significance to these coefficients. There's a lot of math going on behind where these are coming from. If you think about the multivariate Taylor series expansions, right? Binomial factorials, they occur in these multivariate Taylor series expansions. There's stuff going on here as well.
Number of permutations.
So it's right. So here is the formula. And notice there is a 1/n outside, but notice we've got a bunch of factorials. Does this look like anything? Maybe there's a multinomial coefficient coming into play related to something like that. So, again, a huge part of mathematics is pattern recognition. I will sound like a broken record. This is where AI and machine learning is going to defeat us, because they can do a billion, a trillion comparisons, just try everything and find one that works, and then they're done. I mean, to me, it is amazing that computers have learned how to solve Rubik's cubes by just spinning and seeing what happens. And they've taught themselves how to solve Rubik's cubes. They've created moves and procedures. We need to somehow use intuition. Let's multiply by 1 in a clever way. Let's add 0 in a clever way. The computer doesn't have to do it in a clever way. The computer just tries everything. There's a mathematician who writes papers with his computer, and he gives his computer authorship. And depending on whether or not he thinks, he's been doing this for over a decade, depending on whether or not he thinks he or the computer did more work, that's who the first author is. Shlosh B'Yachad is the computer, I believe. And so his computer has its own web page. And just, this is the 21st century. You need to learn how to do stuff like this. So there's a lot of really good stuff that we're seeing today in terms of starting off with something simple. I want to do a matrix. I want to do an exponential function. Well, does e to the x, e to the y equal e to the x plus y? What do I need to prove that rigorously? How do I define sines and cosines? And just thinking back about how things are done. The problem is so many things are done when you're young, you don't notice, and you're not really on guard, and people slip it by you. I'm at least honest. I will tell you when I'm trying to slip something by you. Okay. What do we have to do to rigorously prove the derivative of sine is cosine and the derivative of cosine is minus sine? It's not as easy as you would think. Can we extend it? So this is one of the greatest things in mathematics. If you take a concept, can you push it further? We start off with the absolute value, which represents a magnitude. We then extend it in multivariable calculus or linear algebra to the length of a vector. You can then extend it further to the length of a function. How many of you have seen LP spaces? Okay, if you haven't, it's fine. It's basically just if the integral of the absolute value of the function to the pth power is finite, you then say it's in LP. And you might be over an interval, you might be over all of the real line, you might be in an n-dimensional space. And some functions are in some LP spaces, but not others. Can you give me an example of a function that should probably be in any LP space? 0, right? When in doubt, be a smartass, right? The function that's identically 0. Really don't care what you raise it to, it's still going to be 0. What else do you think might be in every LP space? I'm sorry? Right, so if your interval has infinite length, then a constant would have trouble.
Are we raising the integrand or the integral?
The integrand.
The integrand.
The integrand. So I want a function such that, if I integrate from minus infinity to infinity of any power of the absolute value of this function, I want that to be finite. So the problem with 1 over x squared is it blows up at 0.
1 over factorial.
I'm sorry?
1 over factorial.
Factorial of what?
I mean, does it have to be continuous? If it is not continuous, we can just.
Sure. No, that's fine. You could say, throw away something at the origin and then make it 0 elsewhere.
Yeah.
That'd be fine.
Yeah.
But come on, I mean, if anybody has taken a stats class, you should have a good example. Has anybody here taken any stats? The normal distribution, right? Exponential of negative x squared over something. That has incredible decay. And as you raise it to higher powers, it's going to have even better decay. So, this should definitely be, examples of, things we can take. And so what we did today is we took the matrix exponential and we talked about do properties that hold for real numbers and complex numbers with the exponentials hold where we now use matrix? And the answer was sadly not always. So what we'll do next time is, again, keep emailing me what you're interested in. I'm going to talk about one of my favorite statistics and how it can be generalized. And then the question is, which properties will continue and hold? And so we saw today, unfortunately, that not every property that we start with, we keep. All right, so this is a good place to end.